So now I hope you are beginning to appreciate the problem we are facing. There are these many feedbacks in the system, and some of them can be approximated directly from observations, but most of them cannot be. But you are trying to build models which have these feedbacks, and you want to be sure that the models are doing them realistically. So you have to estimate the feedbacks from the models and then try to find independent evidence that models are doing them reasonably accurately. This is the limitation we face, right? So ice albedo feedback is one of the most important ones on long time scales. Tied in with that is the water vapor feedback, as we said. So this was the long time scale long-term time series from the Vostok ice core. So we are looking here at carbon dioxide levels going back to 800,000 years, and we have already seen this a few times, and I never get tired of showing it and discussing it because it shows very nicely the abrupt time scales you get in the warming phase, where let's say in this case the orbital parameters trigger a retreat of the glacier, and that reduces the albedo, increases the absorption of energy, and makes the climate warmer, and more glaciers melts, and this can go very quickly, very rapidly reach the end of the glacier mass by melting it away. Whereas when you try to build the glacier, as we said, let's say orbital parameters triggered the growth of ice by cooling the temperatures, reducing the energy or the energy distribution. Typically, amount of radiation received at 65 north tends to be critical in terms of keeping the snow on land from one winter to the next, so that more snow can fall on top and glacier can begin to grow. But as that happens, global temperatures begin to cool, water vapor begins to reduce in the atmosphere, snowfall rates begin to decrease, so the glacial growth slows down, but the feedback continues, so that goes slowly and so on. And of course now we are increasing CO2, so instead of orbital parameters changing the energy and the temperature and glacier melt, we are now increasing greenhouse gases first and then looking for how the temperature is responding. And as we said, it is still adjusting because it's still going into the ocean, melting glaciers, evaporating water, and so on and so forth. Okay, so pre-industrial level to 1950 to current level, you can see we are now out of this envelope we have averaged, we have seen for a long time, which is obviously something to worry about. And here are the other things that go with it. Delta O18 shows the measure of temperature, CO2 and methane. We said temperature leads in this orbital forcing case. During glacial times there is reduced precipitation, so dust amount goes up, and then there is the delta deuterium, which is and delta O18. So they are both measures, proxies for temperature. So what do we do with the feedbacks? We already talked that this is a positive feedback, because if surface temperatures increase by some reason, ice and snow cover decrease, so that's a negative feedback. Ice and snow cover decrease leads to reduced albedo, so that's a positive feedback. Reduced albedo leads to more absorption of energy, so negative radiation balance, so that's a negative feedback, and that leads to warmer temperatures. So you have two positives, two negatives, you get a net positive feedback. Remember, we multiply all the feedbacks to get the net feedback of the loop. Obviously it's not that simple, because sometimes you have many other intricate pathways that feedbacks. For example, here vegetation changes happen when ice cover recedes, and that will have a feedback on these time scales. Okay, so here we are looking at ice albedo feedback and two plausible parameterizations of an energy balance model. Here the signs next to the arrows denote the correlation between changes in quantities in boxes, as we already said. The resulting correlation is given in the center of so here we are in the center of the feedback loop, so that's the positive feedback. Self-enhancing process has a positive sign and can therefore lead to instabilities in the climate system. Negative sign corresponds to a damped process, so thermostat is a negative feedback, and this kind of a feedback is a positive feedback. For the parameterization shown in the graph at the right, it's assumed that for low temperatures, a complete snow ice cover exists and albedo is at 0.85 global mean. For high temperatures, planetary albedo of 0.3, which is what we have in the modern times now, right? So models are still not very good at capturing or representing the snow ice cover because land ice models are still very new and we haven't run them long enough, we haven't tested them enough, and there are lots of details. Maybe you will have to include the tectonics, plate movements with the buildup of ice and so on and so forth. So Pierre Sellers in the Pierre Sellers, that's the actor. Okay, Sellers, I think his name was Pierce as well. Peter Sellers was the actor. So Pierre Sellers developed an empirical relation for albedo and temperature change at snow ice cover timescales, which are very slow timescales as we know, and this is valid for range of 222 Kelvin to 283 Kelvin. Obviously have to be below zero. From that we can derive the feedback parameter of shortwave, so minus S0 or 4 d alpha dt. You take this relation and include the d alpha dt, which is 0.009, and you end up with an estimate of 3.08 watts per meter squared per Kelvin as shortwave radiation feedback based on ice albedo process, right? So we take the Planck feedback from before at minus 3.33 and add this estimate to get a net feedback of long wave and short wave at minus 0.25 watts per meter squared per Kelvin. Remember, sensitivity is 1 over lambda, so this obviously increases the sensitivity tremendously of the climate to perturbations, because now you have these internal feedbacks that are able to accelerate the process. What do we get from climate? Climate models estimate shortwave feedback of 0.26 plus minus 0.08. There is a range from different models. That's from Sandrine Boni's and co-authors excellent paper from 2006. So we can say models are doing the shortwave feedback reasonably well, but you can see here that the ice albedo feedback is at 3.08 watts per meter squared per Kelvin. Let's add water vapor feedback to that. Climate models now yield water vapor feedback estimate of 1.80 plus minus 0.8. It's a positive feedback because as temperature increases, water vapor increases. It's a greenhouse gas, makes it warmer, and the other way when you cool it. So that's not easily estimated from observations. So we take models and then we look for evidences that this is a reasonable value. How do we do that? So you take now the Planck feedback or the long wave feedback and the water vapor feedback, and you get a value of minus 1.53 watts per meter squared per Kelvin. A sensitivity 1 over lambda means that water vapor feedback would double the sensitivity because we are going from long wave feedback. The built-in natural negative feedback is the long wave feedback, right? If you warm the planet, energy going out increases. If you cool the planet, energy going out decreases. So you have a negative feedback there. So reducing that feedback increases the sensitivity. And we looked at this before, saying models compared to observations are doing reasonably well in a mean sense. But what does that mean? So this is for a day in May. If we look at other evidence, a good one is to look at the impact of volcanoes, which give a natural large-scale climate experiment. So we already talked about how volcanoes cool the global climate, they also do other things like droughts, redistribution of precipitation, cooling is one of them. The rest is much more complicated. So here are various estimates of satellite data and climate models for volcanic feedback on temperatures. So global mean temperature anomaly in the mid-troposphere at around, let's say, 500 hectopascal after the eruption of Mount Pinatubo in 1991, which was one of the biggest ones in 20th century. A global cooling of 0.7 degrees C was observed with remotely sensed radiation measurements, the microwave sounding unit MSU, and you have to remove the El Nino effect just to be sure, because El Nino is a natural variability, and there was an El Nino following Mount Pinatubo which lasted for several years, and there are also papers arguing that volcanic eruptions can trigger El Nino, but let's not go in that direction. So after warming effect of the 1992-93 ENSO was subtracted, you can see that there is the MSU and there is the MSU with the volcanic El Nino impact removed. So remember that El Nino is taking the heat out of the ocean and redistributing it and releasing it to the atmosphere. So El Nino causes a mini global warming when the event is big enough. And so if you remove that, you see that volcanic impact was much larger in terms of global cooling. And if you take a general circulation model which includes active water vapor feedbacks and give it the volcanic forcing, which is done through aerosols and other ways in which volcanic impacts on radiation can be represented in models. And if you remove the water vapor feedback, you can see that the cooling is not as dramatic at all. So water vapor feedback is a critical feedback, and from this experiment you can go back and say that the value that's being estimated by the models is quite reasonable in terms of explaining volcanic impacts, for example. So this tells us that models are doing a reasonable job of representing water vapor feedbacks, and the model estimate of 1.80 with some uncertainty watts per meter squared per Kelvin can be taken as the good estimate of water vapor feedback. So now we are looking at climate modeling, climate feedbacks, equilibrium climate sensitivity, and addressing the various feedbacks and climate sensitivity, and the challenge of estimating them from observations, and the challenge of making sure that models are capturing those values of feedbacks and climate sensitivities as closely as we can estimate from observations. Multiple issues involved there, so make sure you understand. Okay, let's then look at cloud feedbacks and others in the next podcast.